Good evening, all, and welcome to this first talk of 2025 in the 222nd session of our society. It's great to see such a big audience on a very cold night. My name is Campbell Forrest, and I'm a council member of the society. I just want to check, is the sound volume okay at the back? That's a lot of thumbs. Thank you very much indeed. And you're not all 18-year-old either, so that's a help. Just the housekeeping topics. First of all, toilets are down in the basement. There is one adjacent to the front door. Fire exits, there is no fire drill organised for this evening. Fire exits are at the front here and also down at the back. The front ones are obviously easier to access. If you could check that mobiles and pagers are please switched off or on silent for the good of all your neighbours and everybody else. And to remind you that after the question and answer session, there will be refreshments in the foyer. So to this evening's talk, obviously we had a very late change. Most unfortunately, Mark Williams, who was due to speak, had a serious family illness issue, and I got the email on the evening of New Year's Day. Now, my first thought there was what you say in the quiz show, phone a friend. And the first friend I tried is abroad working this week, so that didn't help. On Friday, I thought, I'll try another friend, but one that I know will not have an off-the-shelf talk ready. And that's when I contacted our speaker tonight, David Webster. And sure enough, David didn't have a talk ready, but he was working on one. And I think it says more than his qualifications and other bits of experience that he simply said, I'll work on it over the weekend and I am free on Wednesday. So, he's here tonight. David has degrees from the universities of Oxford, Stockholm and Strathclyde. But really, he's a hands-on man. He's been an exploration geologist. You'll have seen his CV on the paperwork. And I would have to say he's one of the most energetic people I've ever met in my life. He's built his own house in Islay. He volunteers with Venture Scotland still, David, taking disadvantaged youngsters out into the mountains. And I am so grateful he's here tonight. The topic tonight, David, is Snowball Earth, and it's obviously caught a lot of people's attention. A lot of people would have seen it mentioned on the BBC in the main news programme a couple of months back. And I'm going to invite David now to let us step onto his TARDIS and take us back around 700 million years. On you go.
Thank you, Campbell. Can you hear me at the back? Everything okay? Yeah, sure. Because I will walk about, because I've hopefully got this mic on me now. So, we're going to go tonight to the Garvellach Islands and to Islay by boat. There's the boats that we use to get out to the islands. We have a nice yellow boat and a little self-made landing craft that helps us get onto the rocks out there. So, the Garvellach Islands became quite famous, well known, as Campbell alluded to a few months ago. I can press the right button here, because it got into the news in August. Because we'd written this paper, there's its usual academic, long-winded title. The guy that was the lead author is Elias, and you'll meet Elias a bit later on in the talk, as a young PhD candidate student. And to get a paper in the London Journal of Geological Society as a PhD candidate is amazing. He also then got on the BBC News, which is even more amazing. So this guy deserves a lot of credit for his sort of enthusiasm for it. And I just tagged along with him because I've been working on Islay and the Garvellachs, and I helped him write this paper. The BBC picked it up, as Campbell alluded to. Scottish Islands May Solve the Mystery. The Guardian picked it up with nice pictures, got into all sorts of other worldwide sort of things, and think it was even in the Times. And then it got onto the news, and I'm going to just play a little clip that we clipped from the BBC News just to give you an introduction, and then we'll unpick some of the things. And you'll meet, this is Elias on the top right-hand corner there. And if this works...
Fund could help explain why the Earth entered its biggest ever ice age around 720 million years ago. They say the Garvellachs provide evidence of what led to the period known as Snowball Earth that can't be found anywhere else. Here's our science correspondent Palab Ghosh to explain.
These tiny islands in the Inner Hebrides of Scotland hold the key to how the first animal life emerged on Earth hundreds of millions of years ago. Each layer of this rock face in the Garvellachs captures a snapshot of the planet's distant past. Scientists have now dated fragments of the rock and shown them to be from the only place in the world to have a detailed record of how our planet plunged into the most severe and prolonged ice age in our history. These tiny grains prove beyond any doubt that the Garvellachs are the best and most complete record of a critical period in our history called Snowball Earth, when, for 80 million years, pretty much the entire planet was covered with ice. If we wind back the calendar hundreds of millions of years, we see that Scotland was in a completely different place because the continents have moved over time. It was south of the Earth's equator and had a tropical climate until it and the rest of the planet became engulfed in ice. But then something remarkable happened.
After the melting of the snowball, we suddenly start to get bona fide, modern-looking animals.
It seems counterintuitive that such a big freeze that could have prevented life was actually the spur to generate this explosion of life.
After the snowball melted, of course, everything that had adapted to that and diversified in those specialist niches would have had to then compete with each other in some kind of arms race.
Geologists have been studying the rocks on the Garvellachs for decades, first on foot, using the only building on the island as a base, and more recently using drones to create detailed computer-enhanced images of the rock layers. If the results are confirmed, these islands could be awarded a golden spike. That's an actual spike hammered in to celebrate the location of a planet-changing geological moment. Researchers will find out next year whether they and Scotland have won the golden spike. Palab Ghosh, BBC News.
So we'll try and unpick some of the stuff there. We looked at the zircon crystals that Palab had in his hand there. We'll talk about the golden spike. We'll talk about the theory of Snowball Earth this evening. So the first picture here is the current ice age. This is what we know as the ice age, and this is about as big as it got about 25,000 years ago, looking down on the sort of the northern hemisphere there, with the ice reaching sort of Scotland and northern England, Ireland, Northern Ireland, Greenland, Canada. The 25, and that's a pretty big ice age for the world, pretty dramatic. We were a couple of kilometers of ice over Scotland. I keep pressing the wrong button because that's the pointer one, and this is the clicker. Snowball Earth, we're talking 720 million years ago. So we're going to talk a bit more about time, because geological time is a concept that a lot of people find difficult to sort of get their hands around, or their eyes around. So Scotland was marked by that sort of star, and yeah, the whole world was probably covered in ice, almost certainly covered in ice at certain stages, 720 million years ago. Let's unpick a bit some of why that happened and where we are in time. This is, don't worry about the detail of this, this is the International Chronostratigraphic Chart. This is the International Commission of Stratigraphy, are the governors of geological time. They're the Time Lords. And they define there's a whole process for defining the intervals of geological time. So we don't just use the word Jurassic as a throwaway term when dinosaurs lived. There is a defined rock that marks the start of the Jurassic. There's a defined rock bed that marks the start of the Cretaceous. And when they're ratified by the Commission, they get a golden spike. And you can see the little golden things on the columns there. And Scotland's got two. England has got about 4 or 5, maybe 6, but they're scattered around the whole world. And one of the things we're going to talk about tonight is whether Scotland can get another one. Wrong button. So there's the 2 that Scotland has. We have down at Moffat, we have the base of the Silurian at Dobbs Lynn, and up in Skye in Floddigary, we have the base of the Cymeridian golden spike, where the dinosaur beds have been discovered in Skye. And over to the right-hand side is geological time in deep time, where we're talking about the area of the Precambrian. So we're talking about rocks that are older than 550 million years, which is Precambrian, where life, as we know it, was very remote and very small and insignificant, basically. And you can see there's one golden spike there at the base of what's called the Idakaran, and there's a missing golden spike for the base of the Cryogenian, which is what we're going to talk about tonight. That's a sort of blow up of that corner, and you can see the Snowball Earth periods are 2 or possibly 3 in and around the Cryogenian. Good name for the Snowball Earth period, the Cryogenian. And the golden spike for the Idakaran is in Australia, and you get this little plaque hammered into the rock, or cemented into the rock. And we're hoping that we can get one in the Garvellachs, and that's what we're going to talk about tonight. So let's just wind back a little bit about what the Earth, the sort of states of the Earth, climate states. Most of the Earth's history, it's been a greenhouse Earth with no ice. In fact, that's the norm for the Earth. It doesn't normally have ice. In geological time, there's only been 2 or 3, 4 periods when we've had ice. We call this the greenhouse Earth. The dinosaurs enjoyed the greenhouse Earth. Then we have, occasionally Earth has flipped into icehouse Earth, where we've had ice on the poles, which is currently where we're at. We have ice at the poles. We're in an icehouse Earth at the moment. Very rarely this happens. Yeah? The Snowball Earth, which is what we're going to talk about tonight. This is geological time in a sort of left to right sort of period. So 4.5 billion years ago, start of the Earth, beginning of the birth of the Earth, a long period called the Archean. There was probably an ice age, probably a small ice age around about 2.5 billion years ago. The Cryogenian sort of is right at the end of the Precambrian or the Proterozoic, and then into and I've expanded the Phanerozoic, the later life, into that little bit. And we have the 2 ice ages that we know about in the Cryogenian called the Sturtian and the Maranoan, named after wee places in Australia. Then we have an ice age in the Ordovician, mainly in the southern hemisphere, and another ice age at the end of the Carboniferous, definitely in the southern hemisphere. And then we have the ice age today. So you can see in geological time, ice house is quite rare. Snowball is extremely rare. We think it only happened twice, possibly 3 times, but certainly majorly twice, the Sturtian and the Maranoan. And the debate we've had over the years about the Scottish record is whether it was Sturtian or Maranoan. And tonight, the little crystals that Palab had in his hand are the ones that we hope will convince the International Commission that it's a Sturtian ice age, not a Maranoan one, and therefore helps us with our case for a golden spike. So glaciation. Most times, glaciers, you think of mountain glaciers. So typically up at the top right, we've got a mountain glacial thing. But Snowball Earth is weird because it's got ice at sea level at the equator. Now, here's the equator today. This is Kilimanjaro. That's got ice, but it's at 5,000 meters. Yeah? So we were talking about Snowball Earth more like Antarctica, but Antarctica at the equator with ice shelves, ice grounded onto the continent at sea level. Can you see this cross-section of Antarctica here, where you've got grounded ice at sea level or below sea level and ice shelves extending out? And that's probably what we had at Snowball Earth times, but not at Antarctic latitudes, high latitudes, but at low latitudes too. So this was supposed to be in little animations, but okay, it's okay. So in the 1930s onwards, we got worldwide recognition of Precambrian glacial deposits. So where's my picture gone? Sorry, it's all gone wrong. Never mind. This is trying to do it in a hurry. So we had recognition around the world that were glacial deposits of this age, Precambrian ones. And it wasn't until 1993 that Joe Kersmick, who just disappeared down into the corner there, he coined the term Snowball Earth in a very seminal paper in 1993. And he sort of kind of disappeared off the face of, disappeared out of the literature after that, but he was a very good paper. And the guy that's taken over really as Mr. Snowball Earth is Paul Hoffman. And this book that was that I've just distributed in here, this is basically a biography of Paul, who was a very enigmatic, interesting character, and he's basically driven Snowball Earth. We hear of Snowball Earth today because of Paul Hoffman. He was the guy that really has sort of brought the whole thing academically into the forefront. This is the seminal paper written by Tony Spencer, who you'll hear more of later. 1971, he wrote the memoir for the Geological Society of London on the Precambrian glaciation in Scotland, and it's called Memoir 6 of the London Society. The current team is working on a new memoir of that. In the old days, people did stuff on their own. Academics just worked on their own. Now it's multidisciplinary teams, and a huge new team is doing it. Tony did this as a PhD. He's now in his mid-80s, and he wants to see the new memoir as his sort of final legacy. And he's a great guy to work with. He knows so much about glacial rocks. So we're working with Tony on that. Okay, sorry about that messy slide. It was supposed to be a lot more slick than that. So Snowball Earth, there's a picture of it. Obviously, we don't really know what it looked like. But how did it happen? We think the Earth must have been really cold. It must have been in an icehouse state anyway. It doesn't flip from greenhouse to snowball in a wada. So it must have been already cold. We think the continental arrangements at that time were a bit unique in that we had a supercontinent called Rodinia, and it was all the continents of the world were amassed on the equator with sort of open oceans to the north and the south. It had a weird, some of the modeling suggests that's a really weird sort of ocean current system. We had a big volcanic eruption, we think, at exactly 720 on the equator. Volcanoes do two things to carbon dioxide. They emit a lot, but if you erupt a lot of basalt rock from a bigger volcanic eruption, it weathers, and the net effect is to take CO2 out of the atmosphere. So volcanoes are the key to the regulation of the carbon dioxide cycle in many respects. And so they put out carbon dioxide. They also, their products reduce carbon dioxide. And we think these volcanic eruptions at low latitude pull down CO2 at that point. We also think this eruption, which we'll come onto it a little bit later, in northern Canada, the Franklin, erupted through a load of evaporite deposits and put a lot of sulfur dioxide into the atmosphere as well. We've seen that in the last few years with the reduction of sulfur in diesel fuel, in marine diesel fuel, how that caused some global, the removal of the sulfur dioxide caused warming. So introduction of sulfur dioxide into the atmosphere acts as a thermal barrier and reflects sunlight back, and so it can cause cooling. So you get a lot of snow developing, and then that starts, the theory is that it gets to a sort of the albedo effect, the reflection of the sunlight, then creates a sort of runaway effect, and that is what's caused this snowball. Then you think, well, how the hell do we get out of it? There was a build-up then. The volcanoes don't know about Snowball Earth, they're just going and doing their thing. So there was this build-up, the hydrological cycle had stopped, so therefore the weathering had stopped of the volcanic rocks. So the CO2 was building up, and eventually that global warming overcame the albedo effect. So the two things, so the Earth got itself back into stability again, yeah? There was a rising sea level, and the global Snowball Earth theory suggests that then you get a lot of acidic rain for the high carbon dioxide, you'll get a lot of carbonate limestones and things deposited afterwards with the sea level rise. So you should expect to see that sort of signature in the rock record as well. So this is Paul Hoffman again, standing in Namibia with this thing called a cap carbonate, which is the sort of he and Dan came up with this idea that this showed the end of the snowball. They're standing on what's called a diamictite, which is a rock which if you were out in the fields of Scotland, you'd call boulder clay or tillite. You can see the great big lumps of of rock, and these are what we see today in Scotland. This is from the Port Askaig rocks, and this is just like a big lump of granite in this sort of what was a clay matrix. These are called diamictites. This is another example of one here. So you can see the pink granite thing in the middle there, and this sort of grey mud around it. So Paul looked at these diamictites, so that's the glacial rock, and then above it I've got this cap carbonate, this marine deep water carbonate, which represents the end of the snowball. And you can see it in the Yukon, you see it in Australia, we see it in many places around the world. And as we alluded to in the film there, you saw Graham Shields' arm waving about the start of life as we know it. Yeah? So these sort of clades here of different organisms, how they kicked off after Snowball. Snowball must have reduced the number of bacteria and living organisms to a very small few. Then when the snowball melted, they had the world to explore and diversify. So we are all survivors of Snowball. The Snowball didn't kill everybody off. So some people argue that the Snowball Earth for 60 million years must have killed everything. Well, there must have been places like over a volcanic ridge or a hot smoker, these sort of places where there must have been some meltwater pools, there must have been places where bacteria and extremophiles survived, and then they radiated out once they had the whole world to explore. So where were we? Where was Scotland? So this is a map of what we call Rodinia, 720 million years ago. The brown area is what we call the ancient cratons, the old hard rocks of the world. There's sort of continental shelves around them in the sort of light blue. The dark blue would be ocean. And you can see here the equator runs right through the middle. Scotland is the yellow star, sandwiched between what we call Laurentia, which is North America, basically. ES is East Svalbard, BA is Baltica, which is the core of Norway, Finland, Sweden, and AM is Amazonia, which is the core of this northern part of South America, Amazonia. So they were the sort of major parts of the world at that point, and Scotland was sandwiched in between them in an area that was going to eventually split open Rodinia by an ocean that became the Iapetus Ocean, which grew at that time. And at the time of the glaciation, the Iapetus Ocean was about to open. The Rodinia was about to split open. The other Sturtian rocks are in the green dots, and then the Franklin Large Igneous Province is marked there as probably the sort of smoking gun as to how the Snowball Earth started. Large volumes of basalt erupted onto the equator with the sulfur dioxide plume as well, which we think was the cause. So let's have a look at some Scottish rocks. Let's zoom in a little bit. So the Snowball Earth rocks, the Port Askaig rocks, belong to a group of rocks called the Dalradian, which extend from basically Peterhead, Fraserburgh in the northeast, right down to sort of Connemara and Mayo in the southwest there. And Islay and the Garvellach sort of sits right in the middle of this sort of broad range of rocks. And the beauty of them, as far as people that study these sort of rocks are concerned, is that they're not very deformed. All of these rocks in northern Scotland were deformed in the mountain building event when the Iapetus Ocean finally closed about 470 million years ago, when England came steaming up from the south, collided into Scotland and formed the Caledonian Mountains, and it deformed all these rocks, including the Port Askaig rocks. But luckily in the Garvellachs and Islay, they're not very deformed, as much as they are further to the northeast and into Ireland, and we can see them as they were deposited with very little deformation. So we home in a little bit more. There's a map showing the Garvellachs up in the Firth of Lorne, Jura and Islay. The Jura quartzite, which forms the very prominent paps of Jura, is this sort of yellow band of rock, which is just the band of rock, very thick band of rock that is directly above the glaciation rocks, the Port Askaig Formation, which is where it is brown. So you can see little brown bits up in the Garvellachs. So a little strip there, and there's a few bits and pieces around in Islay and around Port Askaig, which is what it's named after. And we have the Bonahaven dolomite, which is, we will discuss later, which is possibly of a cap carbonate, but we'll come on to that story in a minute, which is that sort of dark blue thing here, yeah, down here. And underneath it is a thing called the Losset limestone, which is below the Port Askaig. So we have limestones below, Port Askaig tillite, diamictite rocks in the middle, and then a carbonate on the top. Nicely exposed here. The upper part of the Port Askaig is on Islay, and the lower part is on the Garvellach, but we can join them all together. Get the right button here. So there's Garvellach, there's Islay. In the old days of geology, going back into the sort of 19th century, these were known as the Port Askaig boulder beds, and you can see here's a picture of a boulder bed, and you can see some of the samples I've got there look like this. They're sort of these little grey rocks with a bit of banding in them, and these great big lumps of granite sticking out of them. And we go back to James Thomson, 1871, and he was the first person in the world to really realize that these rocks were deposited by ice. The language of the day is really interesting. You can read it for yourselves there. He talked about a great northern continent, the gnawing, ceaseless gnawing tooth of time. And then the last word is the interesting one. It's the first time that anybody had realized or just postulated that these rocks were deposited by ice. So the Port Askaig has a lot of historical connotations and interest because it was the first time that this sort of mechanism for rock deposition had been recognized in the geological record. And so it's an interesting sort of snapshot of the late sort of Enlightenment times of geological thinking. So I mentioned Tony Spencer. This is Tony and his favorite islands. This is looking over. This is overlooking the central island of the Garvellach, called Achuli. Like a Neve, the Holy Isle, Saint's Isle, is in the far distance in the mist, and he's standing on Garvellach, the main island. So Tony worked with me in BP for a while, then latterly in Statoil in Norway, having done this PhD, and he wanted to, in his retirement, to go back to the PhD stamping grounds and redo the memoir. And there's the original one, so I've already shown you that picture. And this is the new team. This is the team. There's Tony in the middle there. And we've got a whole team of worthies up there on the rock there, up on the Islay. Elias, who you've met already, down on the left-hand side, and a whole load of other dubious characters. The issue, what we've got is we've assembled a team here of glaciologists like Doug and Mike Hambry, are very prominent, respected glaciologists. Bruce is an Oxford sedimentologist. Ian's a carbonate specialist. Roger Anderton in Gilphead is Dalradian sedimentologist. Richard Waller's a periglacial glaciologist. Alistair's a metamorphic petrologist. So we've got lots and lots of different skills in this. And we are producing a new memoir. Hopefully, I've said this every year, it'll come out this year. But yeah, and we've got each of these main characters will be given a chapter. My chapter is the chapter about where did these granites come from? Because Thomson didn't know where they come. He talked about great northern continent gnawing away and all that stuff. 150 years later, we still don't know where that granite came from. So let's go to the Garvellachs. Garvellachs, depends how you pronounce it. 3 or 4 main islands. I'm going to twist this map round if this thing works properly. I've pinched this slide from Elias, so hopefully it works. Yes, so I've swung it around, and you can see here the sort of Port Askaig rocks are deposited in a sort of linear belt along the Garvellachs. And they were once deposited flat, but they're now all tipped up at 35 degrees. But they're not folded and messed up like rest of Scotland. They're just nicely dipping. They're well exposed. 100% exposure. Most of the problems with geology in Scotland is bracken, midges, bog, all that sort of stuff. But on the western side of the Garvellachs, there's too much rock. There's just rock everywhere. There's nothing covering any of the rock. And you can see everything. And, Elias, you've zoomed it in for me. Well done. Thank you. And there's a picture of the beehive cells. Some of you, Campbell's been there with me. We've been to the beehive cells on like a Neve, Saint's Isle over here. And we've also seen a lot of sea eagles nesting on the islands as well. So a nice place for wildlife. Cetaceans are bombing around the place as well. So a lovely place to go, nice remote place. Uninhabited, there's just, as you saw in the film, there's a wee bothy on Garvellach, and that's it. Here's a picture, just some nice pictures really. This is Achuli, this is the wave cut platform. You can see the 100% exposure of rocks in the cliffs. and on the wave-cut platforms on the west, this is Holy Isle here, and you can see the dip of the rock. The rock is all dipping down to the southeast quite nicely. And you can walk around these wave-cut as you walk around the platform, you encounter successively younger rocks as you go around the platform. So the stratigraphy, the strata, are successively exposed to us as we walk up through the sequence, which is the way geologists like to tell the story from the bottom up. That's looking at Garvellach from our coulee, just a nice picture. Again, showing the dip of the rocks, everything's dipping that way. Bits of bracken in places, but once you get onto the coast, you're fine. That's looking again at like a neve from a coulee with these sort of skerries of Skerletha Cuin in the foreground here. So back to Tony. Here's Tony standing on one of his favourite rocks. This is at the very base of the Port Askaig is a series of carbonate rocks, limestones and dolomites containing calcium carbonate, probably deposited in quite warm equatorial conditions. Think Bahamas sort of conditions. This is a stromatolite, which were the fossils of, well, they were the main life form of the day. They're algal mounds, cyanobacterial mounds, not algal, but never mind. They are mounded developments of life. They are fossils to that extent, and they probably signify that we were in pretty warm water. And these are the rocks immediately before the glaciation. So this is Tony examining a stromatolite in what we call the Garvellach Formation, which underlies the Port Askaig Formation. Geologists talk about formations, which are groups of rocks of the same character. So the Garvellach Formation is a group of rocks that underlie the Port Askaig rocks. The Port Askaig Formation is the glacial rock. Then we have the Bonnehaven Formation above it, which is the end of the glaciation. So we have these three formations. We also, just above the stromatolites, we have evidence of evaporation. These look like birds' feet, but they're in fact gypsum crystals in the mud of this Garvellach Formation, and they also have been taken as evidence of aridity and temperature, and that things were quite warm. Latest thinking is it maybe not quite as warm as originally thought, because gypsum today is characteristic of Sabkhas in the Persian Gulf, and I don't think we're talking Persian Gulf temperatures here, but aridity is certainly a key reason for developing gypsum in the rocks. So these are quite nice. These bird foot sort of radiating star-shaped crystals are quite nice. Then we have, I'm going to mention isotopes once, I think. We do a lot of work with carbon isotopes, and the isotopes of the ratio of carbon-12 to carbon-13 is a very important tool we use in the Precambrian in the absence of fossils. All those golden spikes you saw in the post-Precambrian, in the Phanerozoic, are all based on fossils, first appearances of fossils. We don't have any fossils in the Precambrian that we could use as biostratigraphic markers. Stromatolites look the same 3 billion years ago to today, so they're not much use in terms of working out a time. But we can measure these carbon isotope ratios and correlate around the world. So this anomaly, this carbon-13 excursion, as it's called, here, this is the carbon-13 record. So in the Port Askaig, it's round about 0, but in the pre-Port Askaig, it's much lighter signal, and that was always taken as evidence that the Earth was cooling, because you have lower photosynthetic productivities. Photosynthesis likes carbon-12, doesn't like carbon-13, so the water, it gets enriched in carbon-13. So that sort of thing is a signal. And one of the things that have been taken around the world is that this crossover from negative per mil to 0 or positive per mil readings, maybe that's the place to put the golden spike. Maybe because that's something you can correlate around the world. It's no good having a golden spike that you can't take it anywhere else. It has to be something you could go around the world. So a fossil in Dobbs Lynn in Moffat, you could find that in Scotland, and you can find it in North America, in Greenland, in Alaska, Australia. You can find it around the world because it's a sort of fossil that's extensive and it's time mappable. So without the fossils, we have to think other things. And this carbon, this is now known worldwide as the Garvellach anomaly, and it's mappable around the world. And we've now sampled this bed 38 to the Kingdom Come here, and we know exactly in that bed of rock where the carbon isotope flips over from, it's a really arbitrary point, 0, but it sort of certainly changes from these negative values in the Garvellach Formation. The stromatolites are around, they're down there, down here, the stroms are down here, and then the gypsums were around in here somewhere, and there's more gypsum up here, and then it's a 0 in this bed 39. We've measured every bed, they've all got labels on them. Here's Graham Leslie from the BGS standing on bed 39 with his hand pretty much where the isotope inflection point is on the Garvellachs. This is Dunconnell in the far distance here. This is on Garvellach. So this is the Garvellach Formation, and above it, the rocks where these guys are standing are glacial rocks. This is the end of the carbonates, dolomites and limestones, and then we get into the glacial rocks above bed 39. Wrong button, here we are. The last bed of dolomite has a periglacial erosion surface on it, and it's followed by diamictites. Not quite like these diamictites. The first diamictites in the Port Askaig are full of boulders and pebbles of the underlying limestones and dolomites. It's not till later on in the section, through maybe millions of years later, that the glaciers got so intense they were eroding mountains thousands of miles away possibly, bringing in these exotic rocks. But in the early days of the glaciation, they were just bringing in local rocks, the bedrock. The glacier was just scraping the local bedrock. And there we get, these are the first diamictites in the Port Askaig Formation, just above that bed 38, 39 area. And there's no granites in this at all. All the pebbles in this stuff are limestone and dolomite, and it's a lot of ground up dolomite. Dolomite with a lot of iron in it gets quite brown, so these rocks are quite brown because they've got lumps of brown dolomite in them, and also ground up dolomite rock flour. So they present as sort of quite orangey rocks. Further up, they're much grayer because the dolomite's gone. The glaciers are bringing in all sorts of other exotic rocks from far away. And then we have a very strange boulder bed called the Great Breccia. The diamictites, these rocks are called diamictites. It's the technical term for them, and we've labeled them all with a D number. So we have D1 at the bottom. The first one's a D1. This is D13, and the last one is D48. So we have 48 diamictite beds. So it's not just one bed of glacial rock. It's 48 distinct unit beds. And this is called D13. It's called the Great Breccia because it's got huge big blocks in it. As big as this one. This is what the local boatmen called the bubble, which is a fold. If you can imagine, the glacier has pushed like a bulldozer the rocks in the bed of underneath the glacier and has just bent them right into an overturned fold. So this is enormous thicknesses of ice moving a lot of rock about. It's a lot of rock to move that. And I think I've got a drone picture of that coming up. Yes, this is Doug's drone picture showing that fold. That's enormous amount of energy required to push that rock into that overturned isoclinal fold. So this is D12, D13. And then there's a unit called the main dolomite above that. So there's quite a lot of complicated rocks going on in this D13 area. This is the picture I showed you earlier with the Ilica Neve in the background, our coulee. And the stratigraphy here is quite interesting because we have things called the main dolomite, which is there, and then the Great Breccia is at the bottom here. And this chunk of rock here is a load of the Garvellach Formation, i.e. the older rocks, in what we call a raft. It's just a great chunk of the bedrock below the glacier that's just been pushed up into the glacial rock. And the Great Breccia is full of these rafts. So we're thinking huge amounts of ice, huge thicknesses of ice, pushing stuff about. And it looks like the glaciation has increased in intensity from D1 up to D13. And then on top of D13, we have this thing we've only recently recognized called a jelly fluctite. Don't worry about the name, but these periglacial experts have come to us and said, this is what we would expect to see if the top of the Great Breccia was then left exposed to the air, not covered in ice, but left exposed to freezing conditions for perhaps millions of years. And they then started to think, well, maybe this is the time there was a Snowball Earth, but it wasn't covered in ice. The ice was the Snowball Earth ice did all the pushing, and then it sort of melted away, or it sublimated away, and left a sort of a bare rock surface, like you see in the dry valleys of Antarctica, for maybe millions of years. And this sort of bit of freeze-thaw, bit of down the slope, maybe the snowball, the Great Breccia ice had created a topography, mounds, great mountains and hills, and then this stuff just sort of oozed down the side of it during a major period of time. So we recognize this as possibly as a very severe glaciation event at this time. Above that, we get strange rocks with iron in them. This is iron-rich siltstones called the disrupted beds. They look very disrupted. There's a lot of concretionary dolomite. I'm not going to go into dolomite story tonight, but there's iron in it. And iron is very common in Archean rocks of the old, in the Precambrian. It's very rare in rocks of this age. In fact, it only occurs in the Sturtian glaciation. So we think it's evidence that possibly these rocks were deposited after the sea ice had melted, because if you put sea ice over the whole of the world, you isolate the iron-rich ocean from the atmosphere, and then you suddenly melt it and introduce oxygen and fresh water, and you get iron precipitation. And we think there's a strange chemistry going on here. So this other evidence suggests that something weird happened after the ice melted on the sea. We get these iron deposits. On Islay, just jumping across to Islay, this thing called the breccia at the top of the jelly fluctite, which we call on Garvellach, it's the lighthouse breccia. It's called breccia A on Islay, and that's the breccia where my stick is, and then that's the periglacial breccia, and it's overlain by glacial outwash sands, and then followed by the iron-rich beds. Some are so iron-rich, got magnetite in them, they actually deflect the compass, like the Kulins do. So you've got to watch what you're doing on that part, on some of the hills of Islay, that you don't trust your compass. But we think this is the melting of the ice and the introduction of iron into the system. Then we get lots of lovely evidence. This is back to the Garvellachs. This is one of the beautiful ice polygons. These are freeze-thaw polygon wedges. The freeze-thaw effect creates a polygonal pattern ground type thing. And then we think that the whole place was really, really arid. Remember, you've got a world without plants. Everything, anytime the wind blows, dust comes up. It was a really dusty world. So any of these cracks that open up will just get filled with dust and bits of wind-blown sand. And that's what we've got. We've got this diamictite with granite boulders in them, like that stuff, with cracks in it full of sand and dust. And that's a beautiful sort of example of pattern ground that we see. You see this on Antarctica today, and this is 720 million years old. We get drop stones. This is where floating ice has dropped a rock into the mud, and you can see here the deformation of the rock is so metamorphic deformation, or the folding of the rock is so slight. In places we can actually see the sedimentary layers have been disrupted by this little granite pebble that's been dropped out of a floating iceberg. And we also get things called varves, which are seasonal fluctuations in sediment from summer to winter, and they've been periglacially altered by sort of freeze-thaw action, so they've been bent into what we call involution or cryotubation folds. So we've got lots of evidence of periglacial activities going on. And then we get these granites are in this thing like the samples there, and in places we think the wind has just blown all the dust and the sand away from the mud, all away from these, and just left the big pebbles that the wind couldn't shift. So we call these deflation lags, and the wind has blown away all the fine material. And you can see here, this is up higher in the section. Every pebble there is a great big piece of granite from this northern continent. And they're very spectacular. Yeah, we get into D, remember when we talked about D numbers, so up in higher in the section, D38, everything's granite. Everything's granite. But we still don't know where it's from. But we've got lots of interbeds. This is a picture of Garvellach from Akuli, and we've got these interbeds. The diamictites are the brown layers here. You can see them. We've caught there's D14 to 16, D27 is in here, D33 is in here, and we've got these interbeds of sand. which is why we think this was at sea level. It wasn't, these weren't mountain glaciers. This wasn't boulder clay up on top of Schiehallion or something like that. This was at sea level because when the ice melted, an ice phase melted, the sea came in. So it must have been close to the sea. Yeah? We also think that Scotland, from all sorts of other evidence, was close to the equator, probably 20 degrees south. So we've got ice at sea level near the equator. So that's the sort of the snowball signal, as it were. Even above the D13 level, we've got more and more glacial rock. So that wasn't the end of the glaciation. So this whole cap carbonate finishing off the story doesn't quite work for us in some respects because we have more and more. This is D4, so D13 is around the corner here, 14 to 26, and we can get younger and younger and younger up to the youngest rocks we see on the Garvellachs are about D30 8 times, with these interbeds of sand. And we think these interbeds look like this. This is called the giant crossbeds. You can see here, these are great cross-bedded sets of rock, which you think was a tidal delta, a bit like the Mackenzie Delta in Alaska today. So we've got a huge sort of influx of sand in a sort of marine setting. No ice at all. But there's an ice bed. There's a glacial rock here, D36, and a glacial rock here. So glaciers are happening, but there are periods of interglacial, which is a bit like today. We're in an interglacial now. Who knows when the ice is going to come back again? In Islay, we get some really weird rocks south of Port Askaig. This is a bit of a drone photograph annotated with conglomerates and diamictites. Weird stuff. We think all of this is marine. We think that the water has deepened as the Iapetus Ocean has started to open, and we get weird rocks here. This is Doug driving his drone around. And we get sandstones deposited like this in Islay on Garvellach up near Bunnahabhain, which are marine sandstones. These are definitely marine, and we have a lovely boulder bed on the top with a purple granite. There's the Paps of Jura in the distance, and this is D48, which is the last sign of ice at D48. Above that, we have the stromatolites again. This is in the Bunnahabhain Formation, and this is that stromatolite dome. You can see this is a dome of stromatolites, actually about 2 meters high and 4 or 5 meters across. There's Ian Fairchild, who's the carbonate specialist, and I up on the north coast of Islay looking at these stromatolitic domes. They're some of the best stromatolites, I would say, in the Precambrian, pretty much anywhere in the world. If you ever get to Islay and get to the north coast, it's a spectacular setting for these stromatolites. And this is Shark Bay today, and they look the same. So stromatolites haven't changed a lot in 700 million years or so. We know that probably in the Bunnahabhain Formation, we were back into the warm climate. The glaciers had finished, and we were back into sort of temperate Bahamian type conditions again. Stromatolites were common in the Precambrian because they didn't get grazed. They don't get grazed in Shark Bay because it's very hypersaline and gastropods don't like it, but gastropods would eat most stromatolites today, which is why they're relatively quite rare, but they were the only thing going in the Precambrian. Okay, so why did we think it was the Sturtian? But we didn't know until Elias got his little zircon crystals, and we had indirect evidence that we had it as a Sturtian age, but there was a lot of argument in the literature about whether it was Sturtian or Maranoan. Don't worry about the details, but we had this isotope excursion that I mentioned. We had 3 glaciations across Britain and Britain and Ireland. It looked like, from correlations, that the Islay Garvellachs one was the early one. We had iron, which I showed, and the iron is only known in Sturtian deposits around the world. We have a strontium isotope signal. I said I wouldn't mention isotopes again, but I did. We have a strontium isotope signal from the rocks below, which is very similar to pre-Sturtian rocks around the world. And we have this thing called molar tooth, which I'm not going to talk about. But we had enough indirect evidence that we were pretty convinced it was Sturtian, but there were still papers buzzing around saying, oh, well, there's a date from a Ballyhoonish limestone that's got a 600 million. It means it's a Maranoan thing. So all that sows doubt in the mind of the commission, deciding whether we've got a Sturtian or Maranoan. We certainly can't have a golden spike if we don't even know which glaciation we're talking about. So it just left it there until this summer. So this is Elias's work. These are zircon crystals that he was looking at through his little microscope, big microscope. Zircon is a beautiful mineral. It's a zirconium silicate, but it has an affinity for uranium in its crystal lattice. And uranium, as you know, decays to lead. And if you measure the ratios of uranium to lead, you can work out, using the half-lives, you can work out the age of the zircon. So we plot them, and because there are two decays of uranium, there's 235, 238, and they decay to different leads, 207 and 206. 6. I can't read my own writing. 208. Is it 6 I've written? 206, of course. Anyway, so you can plot them, and you plot them, and then that would actually, most of the granite rocks, if I took the zircons, which are all these zircons in those granite samples there, that would tell me the age of that granite. Yeah? And most of the granites that we've sampled are 1.8 billion years old. So we know that this great northern continent is described. We know how old these rocks, these granites are. They're 1.8. But if you take the actual matrix, the sort of brown grey rock around it, they will have zircons from all over the place. All the rocks that were part of that deposit will be in there, and we get this frequency distribution diagram. And there is the 1.8 million peak. So that matrix has got bits of the granites in it, but it's got other stuff in it. It's got older stuff. It's got Archean stuff in it. It's got younger rocks in it. Young bits of younger rock all mixed up in it as well, so that it tells us something about that. And it also says, well, look, it must be at least 1,000 million years old, because it's got zircons in it that are older than 1,000. So it tells you about the maximum depositional age. But we think that the Sturtian is about 700. So we had we're still a bit unsure as to when we took that sample. We didn't get. These old samples only had 60-odd zircons in the sample. Elias has got a lot more zircons because he's got better equipment, and he can measure a lot more zircons much faster. And he did this is straight from the paper, but he found very young grains in his larger sample sizes, which showed a progressive change up through the section of the Port Askaig from the bottom to the top, which you wouldn't, if it was just a random thing, you wouldn't get this progression. So he reckons that these young single grains are telling him something about the actual age of syndepositional magmatic activity generating zircons into the sediment. And it tells us that these must be about the same age as the sediment, and because of this progression in their ages from the bottom to the top. So this is our proof that these zircon crystals are telling us that the rock is a Sturtian glaciation. So we think it's the right place for this GSSP, Global Stratigraphic Point. The subcommission has been there 3 times. So this spring it's going to get voted on, or spring, summer, and we're the leading candidate. The Garvellachs are the leading candidate for this thing here. These are some of the members of the commission on a trip. And this is the recent trip. We took them, a group of them went with me in the summer to have another look at it. So the news got all this, that actually was a golden spike in the rock. It's wonderful how the news gets it the wrong way round. So we sort of had a bit of a joke about this. When Elias and I were over there, he's an ultra marathon runner, and he sort of lives on sort of vegetables and things, and his lunch was just carrots. So he said to Elias, "Go on, hammer a golden carrot." So that's the carbon isotope inflection point with Elias with his carrot. So yes, that's what we're looking at. Ooh, wrong one, nearly there. So this is summary. This is the last slide, I promise. So we've got 1,100 meters of glacial rock sandwiched between the Garvellach Formation limestones and the Bonahaven dolomite stromatolites. We have this great breccia in the middle, the glacier tectonite as we call it, with big folds in it. We have the iron beds just above it. There's the little red things there. The brown is the diamictite, the glacial rocks, and the yellows are the sandstones. So you can see here we've got this sort of interbeds of sand and diamictite, a kilometre of the rock, across the whole of the two islands. The Garvellach is the lower bit, and the upper bit's from Islay. And you go back to the original slide I showed you of greenhouses and ice houses. So we probably got a sort of greenhouse at the bottom section where you saw the stromatolites and the gypsum pseudomorphs, and then got the big stromatolite domes at the top. Another greenhouse, back in the greenhouse again, and this sort of 1,100 meters showing ice house, and then possibly at the great breccia times in the lighthouse of Breccia, a snowball. But it's not quite the sort of snowball followed by a cap carbonate that Paul Hoffman was describing in Namibia. We have something a bit different. We have a sort of a transgression, or a progression into a snowball, and then a sort of regression out of it, with lots of interglacials between it. So we think we've got a complete record of the Sturtian here, unlike other places in the world, like the Namibia and like Yukon and things like that, where they've just got a snippet of it. There's a lot of erosion at the base of the glaciers, a lot of time gaps, a lot of sedimentological record is a gap rather than a rock record. But we think in this place where we've got this newly opening ocean, the Iapetus Ocean, we have a big hole. And the rocks are just pouring into this hole, and they're not being disturbed. They've just got a nice, beautiful, clean record of rock. And the rate of subsidence and the rate of sedimentation are about balancing. So we've got a nice, clean record. And we've probably got the only record in the world of the transition from the greenhouse into the first ice house and into the snowball and out of it. So we think we've got a lovely story to tell, and the isotope record is there, the zircon record is there. We have the ice. We think that was the ferruginous ocean the ice was taken off the top of the ocean. That caused the iron to be deposited. We don't have a classic cap carbonate. We have carbonates, but they're not the same ones that Paul was standing on in Namibia. They're not deep water carbonates, they're shallow water carbonates. We have a transitional base and a good candidate for a GSSP, for the Clolan spikes, and that's where that might be. That's the golden arrow, and it's a little spike down the bottom there. And we think that the youngest single-grain zircon data prove to us affinity with the Sturtian, not the Maranoan. So we think we've got a good story. We kind of hope the Commission will take notice of it all and see how the voting goes. The only other major candidate is Ethiopia, but it's not very accessible. It's in a war zone. It's up in a big mountainside. Accessibility is part. It doesn't have to be geologically perfect, but it has to be accessible so that people can go and visit it. I mean, arguably the Garvellach's not that accessible, but you can get to them on a boat. You can stay there. You can get there. So yeah, we're kind of hoping that Scotland is going to get the credit for this, and Elias and team credit for it too. If you're interested in this story, there are a couple of books. As I say, Gabrielle wrote a book on basically Paul Hoffman biography, and Graham Shields, who you saw in the video, has just published a book called Born of Ice and Fire, available from all the usual outlets. Yeah, I think that's it. How's the time? Is that all right? I was told that a good presenter should always not just leave a slide up saying thank you and questions. They should leave their summary slide up. So I have.
We could, I'm just going to get the microphones out and we can invite questions. I'm interested in David's definition of accessibility, having just managed to get onto the Garvellach Islands. If you think that's easy. So can we invite a question or two? The one up at the back there.
Yeah. Hi, David. Fascinating talk. The Garvellachs look like a great place to do geology. I've got a question, maybe quite intricate about the drop stones, because I think it's touched upon in the Snowball Earth book. But when you had one of the photos up of the drop stones, the sediment seemed to drape over the top as well. But I don't understand how that would form if the stone has just dropped in. So I guess, I don't know whether that's ever adequately addressed or not. Maybe that's a bit...
Okay, so you're questioning, yeah, you've got, the stones obviously distorted the sediment underneath the sting. Yeah, what you get is what's called a process called differential compaction. So you put mud over the top, but the mud's going to sink and compact where it's just mud on mud, but it's got that rock in the middle. So it's like the Princess and the Pea and the mattress. You remember the whole story? Yeah? So you're always going to feel it. Yeah? So that's what it is. We have a problem that sometimes there's a thing called cleavage or metamorphic foliation, which can disrupt that and makes it confusing sometimes. So there are places where people have said, that's a drop stone, and we said, no, it's not. The metamorphic people have said, no, that's a metamorphic foliation developed. But there are places where that's definitely a drop stone, and it's called differential compaction.
Thanks very much. Question near the front here, I think. We can remind people just to hold the microphone horizontal and close to your mouth, please.
Thank you, David, for a great talk. I maybe missed this, excuse me if I did, but could you tell me how long Snowball Earth lasted?
How long Snowball Earth?
Lasted
Well,
in that condition, Earth in that
okay,
condition.
so on the picture there, I've got it lasting, the ice house from 720 to 660. Okay? Right, that's what... Yeah, and then, but the Snowball Earth, the little red bit at the end, it may have been quite a chunk of that time, and nothing much happened. Yeah? So this is the bit we're working on right now, is to say, well, given that period of time, of the sort of 60 million years of the glaciation, of the 1100 meters of rock, how much of that time was the snowball time? It could have been quite a lot of it, because in 60 million years, you would normally, in a depositional basin, you would normally expect a lot more than 1100 meters of rock. So we think 1100 meters of rock may have been only deposited in, say, half of that time, and the other half was nothing was happening because it was a snowball time. Yeah, the hydrological cycle is shut down. There was no rain, there was no snow, nothing, just a frozen world. Yeah, and that developed this breccia, this periglacial breccia, and then eventually the carbon dioxide, and then we suddenly get back into this cyclicity, of melt back and refreeze and melt back, the Lankovich cycles like we see today, interglacials, glacials. So that whole second ice house was all an interglacial glacial period, yeah, which may have only been 20 million years. So the thicknesses are a bit sort of misleading, because a lot of geological record is gap. Bruce Lavelle, who's one of the sedimentologists, did a podcast recently on Geology Bites called Mind the Gap, which was all about the rock record is mostly gap, which confused the Victorian scientists because they expected to see evolution, all these stages of evolution of creatures, yeah, in the fossil record. You wanted to see progress. But because the rock record is so fragmented, you just see sections of it, little bits of it. And the same applies here. We're just seeing bits of the rock record. The rocks cannibalize each other. The rock just, the glaciers will cannibalize the previous ones, as has happened in Scotland in the last ice age. Okay?
On the way at the back there. Maggie.
Thank you. You said that you still don't know where these granite stones come from. What's your best guess?
Want the 5-minute answer or the full half hour, as the Monty Python joke would say. These rocks contain, the reason we don't know where they came, we know how old they are, but they contain a very strange mineral called chessboard albite. It's an unusual form of feldspar. And we don't see it anywhere in the world apart from a few rare places. We've seen bits in Scandinavia, bits in Labrador, bits in Amazonia. So the jury's out, really. So we know it could be any of those places. Remember the map I showed you where Scotland was sandwiched between Laurentia, Amazonia, and Baltica? They're all candidate places for this type of rock. It may be that it doesn't exist anymore, that the rock record has been destroyed by the mountain building events. We know this is 1.8 billion years old, and the rocks of the Rins complex, which directly underlie the Port Askaig on Islay, on the Rins Peninsula, are 1.8 billion years old, but they're not granites like this. They're cyanites, metamorphosed cyanites. So this has not come from local. This is not a local rock. The original thought was it must be fairly local, but it isn't. So the main candidate to me is probably Rockall. That sounds strange, but there's a Rockall microcontinent sandwiched between Scotland and Greenland. Yeah, it's a microcontinental block, and it's about the size of the British Isles, and it's got 3 boreholes in it. So it's like trying to work out the geology of Britain from 3 boreholes. Not possible. So that rock could exist underneath Rockall. It's an obvious place. It was right next to it was just next door to, and up dip, as it were, upstream of so that we think there's probably a glacial, there's probably some high ground there, but we need to sample it. But the bits of rock we've seen from Rockall aren't this. So what we've seen so far, we have not found it, but it could be there. Does that answer your question there? Not really answer it, but it sort of gives you the idea of what we're thinking, yeah?
Is it a question you had, Colin, just about Gabriel's back?
Thank you. I just wanted to ask from a layman's point of view, you mentioned Northern Ireland as well. So the famous tourist attraction there, the Giant's Causeway, they call it. What age is that? Has that come in to this, what we're talking about?
Giant's Causeway has really got nothing much to do with this story. It's all part of the Staffa Skye Mull volcanic complex, the opening of the Atlantic Ocean.
Yeah.
So here we're talking about opening of the Iapetus Ocean.
So that's a lot younger then, isn't it?
It's a lot younger. The Iapetus Ocean opened, was a fully open ocean between England and Scotland. About, if you were on the planet 500 million years ago, there was 3,000 miles of ocean between England and Scotland. That was the Iapetus Ocean. If you were a dinosaur walking around Skye, you could have walked across Rockall into Greenland, into Labrador. You could have just wandered across there because there was no Atlantic Ocean at the time of the dinosaurs. Yeah? By 60 million years ago, there's huge volcanic eruptions, which is now Iceland, and the North Atlantic Ocean has opened, and that is the lava beds of Skye, the volcanic complexes of the Coolins, Mull, and the basalt lavas of Staffa, Giant's Causeway. They date to 60 million years. Coincidentally, about the time of the asteroid that killed the dinosaurs, but not related.
Hello, thanks for your great lecture. I was wondering, what do you think is the main evidence that the entire Earth was glaciated? Because I understand there's lots of evidence for an ice age, but for it to be snowball, there is the big gap in time, the hiatus that you just mentioned in response to the other question. And then there is this iron deposit, which maybe meant that there is ice all over the ocean. So there's a locked ocean with iron building up and then depositing afterwards. But I don't know, I was just wondering, is that a final argument for the entire world being glaciated, or is there something else?
Okay, so I think your question is that are all the rocks that we see, I had a picture of the Rodinia continent with the volcanic large igneous prominence in the middle and green dots everywhere, yeah, which are all the sort of Sturtian glacial deposits. And you're right, until you date those rocks, you just know that they're Precambrian, but they may not be contemporaneous. They could be isolated at different times, and that was always, people always questioning that. But a lot more work has been done on the dating of these rocks with the zircons. Basically, if you're in good position if you've got the glacial rock, say in Namibia or Mongolia or Yukon, where you've got some ash beds in it, yeah, and that can date it. And there are ash beds in some of the glacial rocks of the Sturgeon. They always are coming out at this 700 million years. So in the last 10 or 15 years, we've crystallized it down to whether they are contemporaneous. Every date comes out the same, yeah. And then it's only this summer we found these dates. There must be some ash clouds around depositing those little zircon crystals, because we only need 1 or 2 crystals. It must be an ash cloud, and that's telling us we've got 720 as well. We didn't know that, but workers around the world looking at their little pet Sturtian glaciation have looked at what they can find out too, yeah, and they've got these dates. They're all coming out around the same. So you're right. You're right to question it. Was it? So we call it a pan-glaciation. Yeah, it's just we think it really was a pan-glaciation. There's enough evidence to suggest they were synchronous. Yeah, and most of it, the paleomagnetic data suggests that virtually every deposit was low latitude, which is why we get this Rodinia low latitude supercontinent with synchronous glaciation on it.
Just at the front here. Just a little. Go back there, Carl.
Thank you. Could I ask about the gypsum crystals that you mentioned that were in the shape of a pattern of a bird's foot?
Yeah.
It reminded me of a rumour I heard years ago that perhaps there were crystals on the Garvellachs that represented periglacial ichthyoid features, and when you mentioned the gypsum crystals there today, you said that they were probably from features from an arid period. Clearly that's 2 completely different things. I'm wondering if these are the same feature that's been represented in 2 different ways or confused in some way, or they're 2 completely separate things altogether.
Yeah. A few years back there was a sort of big ichthyoid sort of zone of interest. Everyone thought that these crystals were ichthyoid. Ichthyoid is a low temperature form of calcite. Yeah, it forms in the bottom of Norwegian fjords and things like that under glaciers. So you get this. Normally you get calcite, and a lot of shells use aragonite. So there's 2 key forms of calcite called aragonite and calcite itself. Ichthyoid is got this weird. It only forms in low temperatures, and people kept saying, "Oh, look, these crystals. They're silica now. They're not carbonate anymore. They've been replaced and they're pseudomorphed because so the quartz the original crystal has disappeared. It's been dissolved away, and the hole has been filled by or replaced by another mineral. In this case, it's quartz. So all we can see is the shape, and it's a blade. And so people looked at the blades, and ichthyoid can have blade forms. Gypsum certainly does have blade forms. But the people who know these things better than I do suggest that the shapes of those are more like gypsum than ichthyoid. But it's not necessarily ruled out. But gypsum, and then because gypsum, everyone says, "Oh, gypsum, it has to be warm." Yeah, but there's talk about remember the ocean chemistry was very different in those days as well. The ocean was not the same as today. With different calcium-magnesium ratios, different minerals are deposited. We get the dolomite with calcium-magnesium carbonates forming at low temperatures, which we don't get today because the ocean was different chemistry. So, yeah, but we think it's gypsum. But you're right to point it out that it might not have been.
Gold is quite a soft metal. How do you hammer a gold spike into solid rock?
I didn't see where the questioner came from. Can you just repeat the question, sorry?
Gold is a soft metal. How do you hammer it into solid rock to make
Believe
a
it
spike?
or not, it's not actually gold. I know you don't believe that. You think I'm really going to go there with a lump of gold, but no. It's not.
And it's harder than a carrot.
Gold, yeah. You know where the golden spike route comes from? It's when the railroads across America were joined up from east to west. It's the golden spike was what was used as a ceremonial joining of the railroads. Yeah, that wasn't gold either.
The Garvellach's a great place to go diving. Is there anything that's under the water that will be of interest to geologists?
Yeah, we've done some dives, to believe it or not, yeah. Not me personally, but we've had divers out there looking for seabed samples because we wanted to understand. I didn't get into that because I could show you some lovely bathymetry maps of the area because we're trying to link the Garvellachs to Islay and the whole Firth of Lorne into Jura to try and map the seabed to see, we're actually going to drill, one of the things is getting money from the Ocean Drilling Project to drill a hole in the Garvellachs, a borehole, a core hole, where we can sample the carbon isotope ratio below the bit I showed you. And I showed you we only have 70 meters of pre-glacial rock on the Garvellachs, where the little Garvellach anomaly is. We think we can drill a hole, and the seabed sampling from the divers has shown us that there are rocks of this Garvellach formation and older ones, obviously out there. So we can drill a hole where we know we start it, we'll spud it on what rocks we know, and we'll core 200, 300 meters. That last trip that I took those Cryogenian people to was part of a workshop to plan a well. So we had money for a workshop to plan the well. We just need to raise the money to drill the damn thing and decide whether it's going to be an offshore well or an onshore well. Will we actually get a rig onto the island, or will we get a shallow water rig and drill it offshore? But yes, diving is good.
Just about what triggered the Snowball Earth. You mentioned the volcanic sulfur dioxide being important in terms of increasing the albedo effect, but could there have been other coincidental triggers such as orbital cycles, increase in oxygen in the atmosphere, and the sun was actually cooler then?
Yeah. So, it's a multi-thing. I mean, there's no one smoking gun for the snowball. Something triggered it. It was already cold. It was already ice house. So it was already on the fringe of tipping. And the Earth often got like that, but they obviously got out of it again. The sulfur is probably quite a key, because it certainly would. It's different. There are lots of igneous provinces around the world with lots of basalts, the Snake River, the Deccan, there's Siberian traps. They didn't cause snowball events, so this one was different. It was on the equator, also no vegetation. So you've got a lot of runoff of water, a lot of runoff into the ocean, a lot of productivity in the ocean, sequestering carbon. So you've got all the conditions are right, and then you've got this sulfur shield as well. And then once you get the albedo effect running away, so it wasn't just one thing, but yeah, I mean, there are thousands of papers written on this, and everyone has their pet theory. They're talking about, it wasn't just the flip, the Franklin one, there was a whole, this Rodinia breakup, there was a lot of volcanic outgassing, there was this, that, and the other going on, lots of things were going on.
We've got a couple of online questions, I think, Geraint.
You mentioned Milankovitch cycles in one of your answers. Are they correlated with the ice ages that you've seen?
That I don't know the exact answer to, but I would suspect that we're seeing cyclicity. We are seeing cyclicity in the record there, so that you would expect that's what the Earth. I mean, some people have speculated, and Malcolm just pointed out, was something else. Some people have speculated that the Earth was a different obliqueness. And the obliquity of the Earth's orbit is certainly responsible for the Milankovitch cycles. It could have been tipped over and be more extreme. We just don't know. There's a lot of research going on in the Paleomag to try and understand a bit more about cyclicity in that period. But yes, we would expect the Earth is wobbling like a spinning top. It's not nice and static. It's doing stuff all the time. And over 60 million years, you would expect to see. We've seen a lot of Milankovitch variation, and we're in an ice age that's only 2 million years old, which is tiddly compared with that 60.
Okay, thank you. And you've illustrated heavily folded rock beds. Are the rocks very hot to allow folding without cracking?
The rocks all these rocks were deformed in the Caledonian orogeny, so they've been heated to about 400 degrees and in about 7 or 8 kilometers, maybe 20 kilometers deep burial. So they've been heated and deformed, but not extreme that they've been melted. Yeah, it's other parts of the Caledonian orogeny chain where the deformation is more intense. You do get, when the rocks are deeply buried, you will get melting of the rock. But we think that here the rocks were they were probably protected by the Jura quartzite, which is the rocks of the paps, a great big blanket of rock over the top. It was like a heat shield, as it were, protecting all these rocks underneath. Because people say, why are the Garvellachs so undeformed? If you go to, if you go to the Cobbler, you see the rocks are all like this. So why weren't the rocks of the Garvellachs all folded and twisted? Because they were protected by this blanket of the Jura quartzite. We know that there are metamorphic minerals in there, biotite, chlorite and stuff, telling us that they were buried they did experience temperatures of 400 degrees, but they didn't melt.
Thank you for a very interesting talk. I just wondered if we know anything about the life forms that made it through this long period of cold.
Yeah, well, you see, I knew I'd get a zoological question, which I probably can't answer. You saw the little diagram I threw up that was one of Paul Hoffman's diagrams that's showing so we had very primitive, cyanobacteria type organisms living at that time. They must have been extremophiles. They must have enjoyed living in very cold waters, but we get those today. We get Antarctica, you get those sort of similar to you get in and then you must have got some bacteria that were living in warm pools, possibly, next to there must have been volcanic eruptions, melting some ice over a volcanic ridge. Things were going on. The geology of the Earth doesn't know there's a snowball above it, so there would have been warm pools where life survived. But under 3 or 4 kilometers of ice, not much would survive, apart from these little pools. Yeah, a lot of work's been done on them. You saw that diagram there, it was sort of biological diagram about, but yes, there is not much survives as a fossil record. That's the problem. In the Bonnehaven Dolomite, we've got some little spherules about a millimeter across that are now got mica in them, and we think they were little prostids? Yeah, little vase-shaped organisms that were sort of, but they're the only ones with any sort of skeleton to preserve. Otherwise, everything, the stromatolites are just, because they secrete and a skin of clay and mud over the top of them. You only see that bit. You don't see the organism itself. You just see the results of what they've built. So we don't know much about the morphology. There is some work done on Precambrian stuff, but yeah,
Time for one last question, if there's anything. Yes, there is, Sheena.
What you've been showing us is the geological evidence for an extraordinary climate phenomenon. And it demonstrates very well, what the history of the Earth's climate must be. But I'm wondering what its relevance has to today. We don't hear so much from climate deniers as we used to since the BBC decided that it doesn't have to give them as much airtime as it does to scientists. But they're still there, they're still out there, and I just wonder what you would say to them about the kind of evidence that you were able to tell us and the kind of changes that the Earth's history has been through.
Yeah, great question. It's sort of, why do geologists do what they do, and why do climate scientists do what they do? Understanding the Earth signal from the anthropogenic signal is obviously an important thing. We need to understand what we are doing, but you need to understand what the Earth does for itself. Yes, the Earth can get in and out of crises, but in time scales that are completely out of kilter with what we need. Yeah? If we stopped emitting today, we have enough volcanic sequestration by weathering of basalts would bring the CO2 down naturally, but it would take 1 million years. Yeah? So we know the Earth can recover from these things, and it has got an understanding the rock record and the isotope record, which is a proxy for temperature, tells us what the Earth was like, which helps us understand what the Earth is going to do all by itself, and then we can add on to that the human signal, and then understand, well, what will happen, what we do. So understanding the rock record is an important part of understanding how the Earth responds to these things by itself. And the Earth, as you can see, we've survived 4.5 billion years. Let's hope we don't really mess it up, I guess. Because we're unique. As Brian Cox said, we're possibly the only sentient life in the whole of this galaxy. Yeah. So it's important to these climate deniers that we tell the story, and we've got evidence here of what the Earth can do by itself, but not in the time frame that we've given it.
Thanks very much indeed, David. I think you learned from my little introduction that if there were any rough edges there, the responsibility for them is mine, not David's, for pushing you into producing this talk in a matter of hours almost rather than days. So this was the dress rehearsal. Thank you so much, David, for a fabulous evening of time travel. And you'll be delighted to receive the greatly coveted Society's digital paperweight.
Thank you very much.
Just before we go down to the foyer to have some refreshments, can I just remind you that the next talk in here is in 2 weeks' time, the 22nd of January. It's Locust Plagues and Other Disasters, Why We Are Made to Survive Adversity by Professor Helen Minnis. Thanks for coming along this evening.